Hello, my name is Anthony, and I'm a master's student here in the AA department. I'm part of the active aeroelastic structures laboratory with Ellie Livney, and I've been here in the department for 2 years now and plan to graduate this summer. It's been a lot of fun and a rewarding experience to work with all these students to transform their knowledge into real engineering products.
Okay, before we get started, I would like to invite the chair of the department, Professor Christy Morganson, to share some remarks.
Great. Thank you. All right. Hello, graduating students. That would be our seniors this year. And welcome to all of our current students, alumni, faculty, staff, family, and friends. Look at this. We're adapting our Capstone Film Festival this year instead of just creating it like we did 4 years ago. Now we're running it partly in person, which is awesome. We're still able to engage our alumni and family and friends who are online, but then also connect together in person as students, faculty, and staff here in our building in Guggenheim. This is the first time we've done this in this room, which is great. This film festival has become a great way for our senior design teams to come together and practice some storytelling about their projects and the impact of these concepts beyond the engineering classroom. So I'd like to give a special thanks to our alumni for coming today, especially those on our alumni judges panel, many of whom have dedicated their time toward mentoring one or more of our ANA students this year. So the members of the panel are Eric Forbes, and I'm not sure, are they here in person? Yeah. They're all online. Oh, I'm so sorry.
I know.
I don't know how to do this in person thing. Very weird. Okay, so anyway, Eric Forbes, Eric Matson, Mike Taniguchi, and Jim Teslo. So thank you to all of our judges who are going to be selecting our Best in Show and our Honorable Mention Awards. They'll be judging the films on accuracy, uniqueness, professionalism, and the potential impact these capstones projects can have on our industry and society at large. So thank you also to our industry sponsors. You have been a big, important component for our project-based education. So thank you to Aerotek, Aerojet Rocketdyne, AeroVironment, Boeing, NASA, and Turion Space. Also want to give a big thank you to Professor Alvar Sanz Otero, who is faculty advisor for all the capstone projects. Also the TAs who you just heard from. So Eddie Ting, Jared Smith, and Anthony Sue. They've all worked really hard with all of the teams this year. And thank you for hosting us tonight. So Alvar, I'd like to invite you to come up and talk about this year's process. Professor Alvar Sanz Otero is our newest addition to the faculty in ANA. Here at the University of Washington, he teaches capstone courses as well as systems engineering. He completed all of his professional degrees at MIT, and then his doctoral research concentrated on the development of space-based microgravity laboratories for operation aboard the International Space Station. He applied his knowledge in electrical engineering and computer science to the development of the Spheres Laboratory, which was up on the space station. We're thrilled to have him here with us to lead our capstone projects. So Alvar, over to you.
Thank you, Christy, and congratulations. We're almost done. I know you'll say, yeah, there's still 2 more weeks, and we're gonna be intense weeks. When I got here almost a year ago, I asked you guys, so who's gonna do a PhD, who's gonna do industry, like where are you trying to measure things? And one of the things that I wanted to understand is where do you guys see yourselves? And the last couple of weeks, as I've seen you finish your capstones and as I've interacted with other people, I can tell you, you are industry leaders. That's what we are here to show, that this is not just about you passing a class, but that as you go into the workforce, you actually know things that a lot of other people will not know. You did Aero Astro. It is one of the hardest majors, and we put you through it. Or did anybody think it was easy? Okay, no hands, good. It wasn't easy, it was very hard. When you go out there, it will show. I have seen it. I've been told by others in the past couple of weeks how you guys got it. And I can tell you that I'm very proud of you, that this is a very exciting moment. I absolutely want to see the videos that you did. But more importantly, I want to see you go out there and be stars, because this is going to show that you are. Thank you. Congratulations. And Eddie, back to you.
Thank you, Professor Morrison and Professor Santero. As I mentioned previously, we got lots of exciting videos, 11 teams out of all the Capstone teams. And each team has videos about their projects on either space or air. And one last thing to mention is the votings. So viewers will be able to vote on the People's Choice Award. So the link to the ballot was emailed this morning to the students, faculty, staff. So we will put the link also on the YouTube, so every viewers will be able to vote. And so if you got more friends, please use them. And also that for the YouTube channels and the Facebook, maybe subscribe, like, and share, because this is your department where you graduated. As we roll the films, that we will roll call on the YouTube chat so we can know who's our old here and watch it. And enjoy and have a good one.
All right. So the first team we have here will be the Aerotek Capstone team, which worked with the Aerotek company, which is based here in Seattle or Washington, to develop a flight analysis and test framework for new aircraft designs. And they're gonna demonstrate their framework by simulating, upgrading, and flight testing an existing unmanned aircraft at an airfield that they select to best fit their requirements.
Welcome to the Aerotek Phase 1 Capstone program. This project is the first of a 3-phase program by Aerotek. The long-term goal for this program is to create a framework where the customer provides an aircraft design to test, the design is simulated using a simple flight simulation, then modifications are applied to the aircraft, and the modified aircraft is tested structurally and in the wind tunnel. Then, the modified aircraft is placed in a detailed simulation, and a flight test performed to qualify the aircraft. Our project, which is phase 1 of the program, has the goal of redeploying at least one UAV from previous UW ANA capstones, implementing the UAV into a flight simulator, and performing at least one successful flight at our chosen test site. To accomplish these goals, the project was split into 3 key sub-teams. The UAV team was tasked with down-selecting 2 UAVs and refurbishing and upgrading at least one into a flight-ready status. The simulator team set out to implement the selected aircraft into a commercially available flight simulator to simulate the flight characteristics and failure mode effects of the UAV. The test site team focused on selecting a test site and streamlining the process of obtaining permission for this project, as well as future phases of the project to safely fly at the location. The first UAV selected was the nose shielding research aircraft made by the 2010 Capstone Group, which is a supersonic configuration inspired by supersonic aircraft of the past such as the Concorde and Tu-144. Powered by a J800R jet turbine engine capable of 17.7 pounds of thrust, the aircraft is capable of a max speed of 130 miles per hour and endurance of approximately 10 minutes. While the 2011 Capstone UAV was also selected, ultimately only the 2010 UAV was chosen to be refurbished due to the time constraints of the project. The aircraft's avionics system was completely replaced, now powered by the Q-Pilot Orange connected to a Hairlink video controller with a 4K 30 frames per second first-person view camera. This system gives the UAV a 20-kilometer transmission range and autonomous flight capabilities. The simulator's goal is to assist in early evaluation of aircraft design by providing an idea of its handling characteristics as well as simulating our test flight and potential failure during operation. For these purposes, X-Plane was chosen for its ability to accurately simulate flight dynamics, its availability of several airports, including our chosen airport in Moses Lake, and the ability to model various failure scenarios, such as having one aileron stuck, both ailerons stuck, or either elevator failing. The test site selected was Grant County International Airport in Moses Lake, which is a 3-hour drive away from Seattle. This site provides capability for future large-scale aircraft of 400 pounds or more and will allow our UAV to fly under FAA Part 107. Our planned flight test date is this Saturday, May 27th, with the nose shielding aircraft will fly again for the first time since 2010.
All right. So our next capstone team is the AeroVironment capstone team. They work with the AeroVironment company to develop a quad rotor drone that can deploy from an AeroVironment Puma LE fixed wing drone. Their quad rotor had to communicate via cellular LTE and navigate autonomously from the deployment location to a destination on the ground.
We choose to go to the moon. We choose to drop a vehicle from a plane. We choose to do this in these 6 months and do the other capstone class things, not because it is easy, but because it is hard. Because that challenge is one that we must accept in order to graduate. One we are unwilling to postpone for more than like a week or two.
AeroVironment tasked this team with designing, building, and testing an aircraft to be dropped from a large carrier unmanned aerial vehicle. Our developed aircraft needed to transmit video via LTE connection, carry an 1/8 of a pound medical payload, hover for at least 10 minutes, weigh less than 2.75 pounds, and fit within the space constraints of the carrier UAV payload bay.
The team developed the Jellyfish delivery system, which utilizes a Pixox 6X flight controller with autopilot software and a Raspberry Pi to relay flight data and a video stream over the internet to the ground station. The Pixox uses a PID feedback loop from GPS, accelerometer, and gyroscope sensors to maintain stable autonomous flight. The Jellyfish arms fold 90 degrees downwards and automatically open upon deployment due to 180-degree torsion springs. 3D printed clevises provide the connection between the Jellyfish body and arms. 2 platforms constructed of carbon fiber honeycomb sandwich panels house all electronics and the payload.
Quadcopter flight duration depends on many variables. We chose 3-blade folding propellers to maximize our thrust efficiency within the Jellyfish size constraints. We mounted these to brushless DC motors powered by LiPo batteries.
The Jellyfish is secured to the carrier UAV using a hook and pin system. The hook is attached to the Jellyfish and the pin is actuated by a small servo. The Jellyfish has completed testing and is ready for further development. A combination of 6 deployments and recoveries from the carrier UAV and ground testing led to satisfaction of all system requirements. The test results showed the Jellyfish could serve as a critical tool for delivering time-sensitive medical supplies to people in remote areas and disaster relief zones.
All right. Our next capstone team is the Boeing Utility Freighter capstone team, which worked with Boeing to develop and wind tunnel test a clean sheet design for a regional freighter aircraft. The aircraft is designed to serve a gap in the market for aircraft that can carry standard sized cargo pallets to small regional airports.
Right now, air cargo makes up 35% of all global trade by value. Air cargo transportation is only expected to increase through the mid-2040s, but there is a bottleneck for air cargo's expansion. Currently, it is prohibitively expensive and cumbersome to ship to small outlying airports. This is because small cargo aircraft just can't handle the universal loading devices, or ULDs, that larger aircraft use. In order for a new airplane to be competitive in this market space, it would need to have the ability to transport and handle these ULDs quickly and efficiently. we were tasked with creating a preliminary design for such an aircraft, and with the help of Boeing, the AA department, and our faculty mentors, we are pleased to say that we were successful.
For this utility freighter, we had proposed a design of a high-wing, twin-turboprop, T-tail aircraft with a high aspect ratio.
Decision for the aspect ratio was based off of our requirements, being the span should be limited to 118 feet. Because the higher the aspect ratio, you would get more efficiency out of the wing. From our analysis, we determined the aspect ratio turned out to be 10 to 12.
To validate the structure design, the aircraft aspects such as fuselage, wing, payload deck, structures analysis are through the finite element analysis.
The aerodynamics department, we used OpenVSP because it runs fast. The software would help us predict the performance for the lift better as compared to the drag.
In order to validate the aerodynamic predictions that we made with OpenVSP, we decided to make a wind tunnel model that we tested in the 3x3 wind tunnel here at UW. And so to do that, we took the mesh of the aerodynamic model that we had been using in OpenVSP, and we sliced it up in SolidWorks to make a bunch of individual components that we then 3D printed and epoxied together, and then mounted those to a sting mount in the 3x3 wind tunnel, and used that to get CD and CL data.
Speaking of our status, we have completed a preliminary design and tested in the wind tunnel. And by next week, we will complete our acceptance review. The Boeing utility freighter hope our proposed solutions will bring a great impact to the air cargo industry in the future.
Our next capstone team is the Empowered Startups capstone team, which works with the Empowered Startups startup incubator based here in Washington to develop a quadrotor to collect data on environmental conditions. And this data can then be used to detect and predict climate disasters such as wildfires.
The next teams will be the Scalos team, what stands for the supersonic configuration at low speeds. This year, Capstone team are part of a bigger project funded by NASA commercial supersonic technology program, building an aerodynamic data bank for public access and future use for bringing back the commercial supersonic travels. Please enjoy me watching the videos.
Introducing the Scalos project, a 4-year research study at the University of Washington with one mission: to build a database of low-speed characteristics for different supersonic aircraft configurations. We aim to provide tangible data to aircraft designers that can be used during the crucial preliminary design phase. The project is divided into 2 initiatives, focusing on wind tunnel testing and conceptual design respectively. The wind tunnel testing initiative focuses on mapping the low-speed design space of supersonic transports using the University of Washington's Kirsten Wind Tunnel. The conceptual design initiative is a preliminary aircraft design focused on utilizing the data collected from wind tunnel testing. This analysis is used to further develop a reference supersonic airliner configuration, or RSAC.
This year, during the wind tunnel testing initiative, the team performed a staggering 438 runs, measuring all 6-axis forces and moments at various dynamic pressures. A large focus of testing was terrain interference data collection to improve the accuracy of past and future measurements. This testing uses a series of specialized runs to quantify and eliminate the effects of model mounting equipment. Additionally, the team designed a series of novel leading-edge devices and manufactured them in-house. These parts were evaluated on existing wing structures to provide insight into making wings more effective at low speeds. Furthermore, a low sonic boom configuration, similar to existing industry-proposed supersonic configurations, was tested. On the conceptual side of the design process, the SST team iterated wing sections by using wind tunnel data, and then adjusted the shape to produce a final optimized wing. Another goal of the conceptual design process was to develop a MATLAB script that utilizes discretized aerodynamic equations to generate performance parameters for a full-scale RSAC model. This analysis was used to validate mission range capability and assess factors like takeoff approach noise and relative emissions footprint.
Now with the data acquired, the team is processing over 400 test runs to analyze results and add them to the database. This consists of tracking down relevant test runs and comparing them against each other to determine which model configurations perform the best. Using these evaluations, the team will add to previous year's results and make generalizations on how different configurations affect the aircraft's low-speed performance. Armed with the data we collected, designers will be able to make informed decisions that shape the future of supersonic flight and one day bring us back to Mach 1.6.
All right, now on to the space team. So first up, we have the Husky Satellite Lab Moon Thruster Capstone team, who worked to create a prototype of a cold gas thruster propulsion system for their eventual Husky Sat-2. This is a key stepping stone in developing a cold gas thruster that will eventually be part of a satellite that HSL wants to deploy from NASA's Lunar Gateway.
The Husky Satellite Lab is sponsoring one of the capstones this year. It's a moon-related capstone. How is it moon related? Well, it's called a moon thruster. What does a moon thruster do? Well, we're going to find out very soon, but it looks pretty darn cool. So first of all, a bit more about the sponsor of this project. The sponsor is the Husky Satellite Lab at the University of Washington. The Husky Satellite Lab is composed of a bunch of students. You might not know what we're doing, but we're sure passionate about space, and we build satellites that do go to space. So where's this project actually going to be applied? What clients are going to use it? The Husky Satellite Lab has some upcoming projects that are going to make use of this type of thruster. The most immediate one is HuskySat 2, which will be a technology demonstration of the stuff done in this capstone in preparation for HuskySat 3, a moon mission. Now, what are the requirements for this moon thruster that we're working on? Well, the primary objective is that it needs to prototype and ground test a cold gas thruster that can get HuskySat 3 from a near rectilinear halo orbit down to low moon orbit. One of the secondary objectives for this mission is to be compatible with the HuskySat 2 satellite, so that it'll be easy to integrate and demonstrate in space. Additionally, we want to document this project thoroughly, so that future teams have an easy time replicating our results and building off our work. So who's building this on this capstone project? First of all, we've got Mitsuki. He's our propulsion expert and knows everything that there is to know about rocket engines, to some extent. We also have Oliver, who knows everything there is to know about thermodynamics, and William, who knows everything there is to know about structures. Alnus is a physicist, and perhaps he sometimes does useful things, but we're not really sure. There's also Sarah. Sarah does propellant transfer analysis and battles with suppliers. On the right we have Brad, who does manufacturing, and not pictured is Stephanie, who does propellant storage analysis and design. The first part of our design process was conceptual design. We did high-level trade studies and analysis of various alternatives for the overall concept. Then we went into detail design, so that meant a lot of CAD, and even more CAD to design everything. After that, we went into manufacturing. Making chips fly, it's so great to see things coming together physically. So, a lot of fun, but unfortunately it happened at the last minute a little bit, as well as integration. So when does it all come together? Well, unfortunately we had some big shipping delays, of the order of 4 weeks. So here's a cool screenshot of the CAD model that you can look at, and hopefully we'll have the propulsion system running soon. The main technological contribution that this project makes is it makes space easier in terms of giving an open source base for rocketry research. It additionally makes an economical impact by making rocketry cheaper to access for university teams. Additionally, the environmental impact of this engine is some 10,000 times smaller than some alternative propellants. Finally, on the social impact, it's making space more available by making space research accessible to undergraduate students. Thank you everyone for watching, and we would love to thank our advisors and supporters.
All right, next up we have the NASA Suits Capstone team who worked with NASA as well as some students from other departments to create an augmented reality system for space interfacing with real-time data and surroundings for human lunar missions using the Microsoft HoloLens.
In recent years, NASA has developed an application in augmented reality, or AR, to assist astronauts in the tasks on the International Space Station. NASA's next mission is to develop an AR environment for deep space missions, which led to the beginning of the Suits Challenge. For this challenge, the NASA Suits Capstone joined the UW Astro Huskies team in designing and creating spacesuit information displays within AR environments for future lunar exploration missions.
Our team consists of primarily two groups, designers and developers. Our capstone kind of fell more into the development side, but we each had a hand in the design as well.
The primary dashboard implements all of the different features of the application. This includes a telemetry screen with live updated data of the astronaut's vitals, a mini-map of the astronaut's surroundings, the astronaut and autonomous rover navigation modules, the alerts submodule, the UIA egress procedure submodule, the spectroscopy submodule, and the task management submodule. This interface sits above the primary view of the astronaut, which includes a compass and the alerts tab. While constantly looking up, you might experience neck strain, so you have the option to bring down the menu to your field of view if you would like. This can be easily manipulated by the astronaut.
The navigation module consists of 5 principal components. The first component we're going to talk about is the waypoint system. You can place waypoints by coordinates or at your current location. It can be visualized on our second component, which is the mini-map. They appear as red markers on the minimap, and you can see your position relative to these waypoints. You can also see a trail marked out on the way you took out from the home base towards these waypoints. The third feature we implemented is navigating to the waypoints themselves. There are two principal ways you can do this. One, there will be a trail that appears in front of you that will lead you to the waypoint in the optimal path. And two, interacts with our fourth component, which is a compass that appears on your HUD. If you're currently navigating towards a waypoint, it will take you to that waypoint by putting a red marker in the direction in which way you have to go. Lastly, our last feature is a breadcrumb trail, which allows you to navigate home the same way that you took out to your home base, which ensures that the astronaut is always able to safely navigate home.
One of the unique features of the challenge this year is implementing a method for astronauts to be able to control a rover during their lunar excursions. The way that we implemented this is we designed an interface so that the astronaut can easily send the rover via multiple methods, including inputting coordinates and using saved waypoints. We also have a feature so that the rover can be recalled to the astronaut's location, and a safety feature so that the astronaut can stop the rover in case it is necessary.
The highlight of this project was that we got to fly out to Houston to actually test our application on site at Johnson Space Center.
Since we had a week there and 2 official testing days, we got a chance to fix things that didn't work and implement some suggestions given by the test pilot on the first day. In 3 days, we went from having only one function working to all modules and features integrated and working correctly, and we're the only team to achieve that out of all 10 that were in attendance. We also had a really fun time getting to explore Space Center Houston and presenting our project to the general public in the atrium.
All in all, this is a really fascinating and just straight up fun project, and I'm really excited to see this technology actually on the moon in the next few years.
Next up, we have the SARP nose cone capstone team, who worked to develop a process for creating a filament wound nose cone for SARP's rockets using the X-Winder. This will enable SARP to more efficiently manufacture nose cones and provide the flexibility for changing these geometries in the designs.
Once upon a time, there was a composite filament winding machine called the X-Winder in a naive capstone team that thought they could fix it. This team was made up of 6 members of the Society for Advanced Rocket Propulsion, also known as SARP. SARP is a student organization at the University of Washington dedicated to developing high-performance rockets that incorporate technologies and processes relevant to the launch industry while building student engineers' skills. The optimal nose cone profile depends on the flight profile of the rocket, which is highly variable during the rocket's design phase. Currently, SARP nose cones are manufactured by laying up 2 nose cone halves on a female mold using pre-preg fiberglass. These halves are then combined with a wet layup lap joint. This process is time-consuming, highly prone to human error, and requires expensive molds that cannot be easily redesigned to accommodate nose cone design iterations. Shown here is SARP's solid propellant-powered rocket with the only nose cone shape that can be manufactured using SARP's existing manufacturing abilities and materials. This nose cone was optimized for a longer, liquid bipropellant rocket with a different flight profile. Shown here is the same rocket with a nose cone better suited for its length and flight profile. This flexibility and nose cone design would be enabled by our process. The X-Winder is a desktop glass or carbon fiber filament winder and was proposed as the basis for an alternative nose cone manufacturing method. This winder was previously used to manufacture skirts for SARP's composite tanks. Our proposed manufacturing process consists of laying composite filament over a 3D printed mandrel. This mandrel is then dissolved out after curing, leaving only the composite layup. This is then trimmed and sanded to produce a final flight-worthy nose cone. The X-Winder has proven to be extremely unpredictable and unreliable. Wind attempts consistently fail as shown here. Even when executing the same G-code, the X-Winder will fail in different places. Here, the delivery head deviated from its intended toolpath and collided with the mandrel. Here, the delivery head seizes up and moves too far inwards. Bruh. Our initial challenges printing dissolvable filament were eventually solved. Despite the X-winder's limitations, our process for manufacturing nose cones would still be operational if a better filament winder was acquired. All other stages of the manufacturing process were tested and verified, including mandrel production, dissolvability, and post-processing. We'd like to give a special thank you to Alvar for his guidance and support, Kevin from the Chemistry Machine Shop for his hands-on expertise, and Cadwine for the generous software donation.
Now we will see the SARP electric pump capstone team who worked to create an electric turbo pump for SARP's Star Gazer rockets. The use of an electric turbo pump will reduce the needed mass for the rocket by eliminating the need for a pressure tank and accompanying plumbing and airframe.
In the vast expanse of the aerospace industry, a team of brilliant young minds has taken on an audacious challenge to design and manufacture a 3D printed electric pump for SARP's future rockets, beginning with a test pump scaled for the high-spirit subscale engine. The team will leverage cutting-edge manufacturing techniques, advanced design software, and improvements to battery density to make an electric pump feasible for flight to the edge of space. Introducing the SARP Electric Pump Capstone team. The team sets out at once and begins their extensive research and analysis. They explore the new potential of electric pumps, which offers advantages over pressure-fed and turbopump systems of yore, such as improved efficiency, reduced weight, and enhanced control. An advanced software named CF Turbo is used to meticulously design the rotor that acts on the fluid in the pump, known as the impeller. Every detail is tweaked to specifically match the desired performance the team needs, offering great efficiency. The flow of fluid through the pump is simulated in Cimerix, confirming the results of the work done in CF Turbo. With the design finalized, the team begins their mad dash to manufacture their components. The impeller and volute is sent out to proto labs for 3D printing. The drive shaft and pump structure containing a variety of bearings and seals is machined down to the smallest of tolerances. A custom-designed PCB handles the data coming in from the pump's many onboard pressure transducers and thermocouples. An Arduino allows for the speed of the motor to be controlled along with an integrated tachometer so that the pump knows how fast it is spinning at all times. A rigid test stand is built along with the fluid systems that support the pump with enough water to run the pump for 45 seconds. The drive shaft and impeller are finally balanced by balancing service company, and the pump is assembled. With the pump assembled, the team begins testing of the motor system and the rotating assembly. The pump's oil reservoir is filled, and the team follows their strict safety protocol to protect themselves from the assembly rotating at a blazing 28,000 revolutions per minute. The command to spin is sent from the control computer and the motor sequence begins. A great success. The target is met and the team is jumping for joy. What's next, you may ask? Next is to fluid test the pump with water and achieve a pressure of 450 psi with a flow rate of 0.5 kilograms per second. And for these students, these engineers' work will be continued by their successors in SARP while they go on to tackle new challenges in the space industry. Space exploration is in good hands with these bright minds who will work to show the world that anything is possible with enough courage and enough elbow grease.
And our last SARP team is the SARP Reaction Control Systems Capstone, who created a scaled prototype reaction control system for SARP Star Gazer rockets. This system will provide increased stability to the rocket through active control with that instead of using larger fins, which would increase the drag.
We are the Society for Advanced Rocket Propulsion, and in 2025, we are going to space. Okay, we're not sending actual people to space. Instead, we're building an uncrewed rocket that will go faster and higher than any rocket we've built before. Our rocket will accelerate up to 4 times the speed of sound in 30 seconds. It'll fly straight up more than 100 kilometers in 3 minutes, crossing the edge of the atmosphere and reaching space before it falls back to Earth. Its name? Stargazer.
Hey, I'm Avi Mithil.
Hi, I'm Allie.
Hey, I'm Ramin.
Hi, I'm Evan.
Hi, I'm Josh Chain. I'm the controls engineer.
I'm the propulsion engineer.
The avionics engineer. I'm the structures engineer.
I am the systems engineer for the
SARP
SARP
RCS Capstone.
For Stargazer to hit 100 kilometers, it needs to fly as straight as possible. Usually, that means using fins. But at these speeds and altitudes, fins just aren't enough. Enter the reaction control system. When the rocket deviates from the planned trajectory, tiny thrusters in the nose create short pulses of compressed gas, pushing the rocket back on course. These thrusters take up some of the burden of stabilizing the rocket, which lets us use smaller fins with less drag. Our team is building a subscale prototype of the Stargazer reaction control system to take us one step closer to space.
The scaled model is tested on our 1 degree of freedom test stand. This is used to characterize our thrusters as well as tune our controller. Our thrusters are capable of producing 12 newtons of thrust each. These are using nitrogen gas as our propellant.
Our test stand is almost 50 pounds. The reason is so that our 1/10 scale thrusters can have the same control authority as the full scale thrusters are going to have on Stargazer. As far as the control software is concerned, it's controlling the real thing. Our software uses a PID controller. This algorithm considers where we are, where we've been, and where we're going. From that, we can figure out how to push the test stand angle back to vertical and keep it there.
Firing. With our subscale prototype, we've shown that a reaction control system for Stargazer is possible. We leave it to future engineers to continue our work to scale our system up by a factor of 10 or more and to launch it into space. We're confident that they will keep Stargazer on course, and we can't wait to see them at the countdown in 2025. 3, 2, 1.
And our final space capstone, the Turion space team worked with the Turion company to design, build, and test a debris removal prototype that can survive a space-like environment. This prototype will inform Turion on their capture mechanism effectiveness and capabilities for future LEO debris cleanup.
Near-Earth space debris, or space junk, is an issue that grows in magnitude and urgency every day. Since humans first started exploring space in the 1950s, the amount of debris in low Earth orbit has increased exponentially. In fact, as of 2021, NASA and the DoD are tracking over 27,000 pieces of debris that they consider a threat to manned or robotic space missions. Luckily, Turion Space is working on a solution. They're designing devices to perform active debris removal, a process where space debris is actively removed from orbit as opposed to waiting for natural processes to drag it into the atmosphere. Turion's devices will consist of CubeSats that will track down and attach to space debris and then bring the debris to a lower orbit where Earth's atmosphere can do the rest.
With our testbed, Turion Space will be able to place their CubeSats in a thermal vacuum chamber and run a number of tests on their capture mechanism without ever opening the door. Our apparatus will also collect video and accelerometer data from each trial that allows Turion to analyze the effectiveness of different devices for capturing free-floating debris.
Our testing equipment consists of 3 main parts that will be placed inside a thermal vacuum chamber: the debris vehicle, the end effector vehicle, and the mechatronic system, as well as a GUI program and computer to run the tests externally. The 2 vehicles simulate an in-orbit capture by gliding across a testing plate and colliding at low speeds. The end effector vehicle holds the Turion design capture mechanism, while the debris vehicle holds simulated space debris. They also record and wirelessly transmit data on forces, acceleration, and rotation during tests, and have multiple configuration options for both the debris type and capture mechanism orientation.
Beneath the 2 vehicles is the mechatronics assembly, which contains stepper motors and electromagnets that can magnetically grab and reposition the vehicles between tests. The mechatronics assembly also allows for custom orientation and positioning for each trial to test different approach angles that may rise in orbit. These parameters are controlled through a GUI. This communicates with the Raspberry Pi, which serves as the main computer of the overall system, and 2 Arduinos, which directly control the stepper motors and electromagnets.
Most of our parts are machined from aluminum, as vacuum chambers have stringent outgassing requirements that eliminate the ability to use other materials like wood or plastic. Since every part has to be made of metal, our manufacturing was accomplished using tools like the bandsaw, mill, lathe, and water jet. Now all of this will culminate in our final assembly, which Turion Space will use to validate the functionality of their debris removal system, bringing us one step closer to solving the space junk problem.
To those online, thank you for watching. Thanks, Professor Morganson, our alumni judges, panels including Eric Ford, Eric Mattons, James Taslow, and Mike Kanichi. Thank you so much for our industry sponsor, Aerotek, Air Environment, Boeing, NASA, and Turion Space, and of course, all the Capstone team members for accomplishing your guys' work. That's this year, and remember to vote. Thank you.